real dielectric plates. But as we know, the most important restriction of the theory is the fact that in closed form expression can be only given for parallel plate. But most of the experiment, and also our experiment, has been done in the sphere plate geometry to prevent the problem of the parallelism, which by applying the PFA on plate formula, we can have an approximation for Lifshitz form. But why we selected, why is the important Casimir force? Casimir force, it seems difficult to imagine that the force so weak and hard to detect likely to be significant in application, either as a problem or as an opportunity. But microelectromechanical system, they have a right size for the Casimir force to exert because they have a big size, area and a small gap which can pull components together and lock them permanently, which we know this malfunction as a distinction. By miniaturization toward the nano-electromechanical system, the distance the distance between the elements has become shorter, so therefore the forces become more dominant. And another factor, as I presented here in this graph, you see that if we consider the typical applied voltage for NEMS 0.1 volt in the range below 100 nanometer, Casimir force can be dominated. Therefore, a correct estimation of the force for analysis and design of the nano-electromechanical system is inevitable, especially if it's including the complex material system like silicon carbide rather than just metal. But here, why we selected silicon carbide to study? Now we have an increasing demand for sensors that can operate at high temperature metals are not always suitable for this situation, especially if attributes like high durability combined with low thermal expansion are necessary. Candidates for this situation are silicon carbide and gallium nitride. But in order to benefit from the enormous knowledge we have from silicon IC technology, attention is first directed to the silicon derivative or silicon carbide, which is now using in precise instrumental frame and mirror, and because of a large electronic band gap in high power and high temperature electronic. So there are some, a lot of the research has been done. I presented some of them here, which they use that as a resonator, which can work in the order of even gigahertz, and because of unique optical property of the silicon carbide also make it ideally suited for optomechanical devices. So this schematic of AFM we use for force measurement. We have gold-coated sphere interacting with silicon carbide plate. But since both samples are hydrophilic, vapor condensation and formation of the capillary meniscus lead to surface jump to a contact and prevent the cantilever from retraction, despite we use the several micrometer ramp size. So the problem can be solved by pumping the system down to the 10 to the minus 5 millibar and venting it several times with dry nitrogen. So one should keep in mind that even with all of this drying, venting several times, with the dry nitrogen still we cannot fully eliminate the thin water layer. So at this stage we decided also to have a comparison between the van der Waals Casimir force and capillary forces, which is very important in the ambient condition. So this is the typical result cantilever deflection versus piezo displacement we have from AFM, as we see for Casimir van der Waals force, we have the cantilever deflection around 10 nanometer, whereas this is different order of the magnitude for the pull-off adhesion forces. When pull-off adhesion forces depend on several factors like humidity and roughness, but here I just presented some part of the experiment we have done to show the effect of the roughness. Here we see that this graph, capillary forces independent of this sphere roughness, independent of the sphere radius versus the RMS roughness. As we see here, up to 8 nanometer, we saw that there is no significant change in capillary force, which shows that the capillary meniscus is formed over large contact area of the sphere and plate, which, as we can see in this schematic. But by just extra 6 nanometer increment in the RMS roughness, the force decreased nearly by 2 orders of the magnitude, which which is in good and close to the theory prediction which we used Kelvin equation. So this low value shows that the capillary bridge just formed in some asperity for a sphere plate geometry. From here, I want to focus more for the process we use for Casimir force measurement. So here we see that the cantilever and the spheres under optical microscope of AFM, we use the sphere, borosilicate sphere with the 10 micrometer radius and attached it to the cantilever. So it's a little bit tricky and time consuming process, should be also a little bit lucky to get clean sphere and with a smooth interaction slab. So after this, here I presented from 2 of the cantilever SEM image of the sphere, which glued on the tip with the both at same radius, 10 micrometer. Measurement of the Casimir force for silicon carbide, as for any other dielectric material, is complicated by trapping of the electrical charges. So the problem can be significantly reduced by doping of the material, which make it slightly conductive. Here we have experimental data we got from ellipsometry in short range frequency from silicon carbide. I put it also gold because it's most used material in the experiment to see to have an idea how difference there. Or here we have this peak for silicon carbide because of effect of the surface phonon polariton in the range about 11 micrometer, which was the property which make it suitable for optomechanical devices. By using Drude model, which corresponds to the charge carrier, we extrapolated the dielectric function in the large frequency domain, which we need in the imaginary part to calculate the Casimir force in the Lifshitz, via Lifshitz theory. So prior to the force measurement, we did the topography of the both silicon carbide plate and gold-coated sphere. So silicon carbide is almost flat, and as you can see from this graph, and the most contribution from the roughness is coming from the sphere. So this, by extracting the data from AFM and considering the high distribution, we can have an estimation for minimum distance upon contact. So this number, this very low number we had here, which allow us to approach at the separation below 10 nanometer, which just limited by jump to a contact. So we know that from, as in the morning we had from the presentation of the Omar Moheddin also here, I mentioned that here the typical graph we got from the AFM, so we have cantilever deflection versus the distance. But to translate the cantilever deflection to force, one has to know the spring constant precisely. So using the thermal tuning give us the spring constant with accuracy about 10%. So if we want to have more precise, which consequence then more precise number for the force, we can use the electrostatic calibration. So this formula is using for electrostatic force between the sphere and plate. So we apply the different voltage and we measure the force, and in the range above 600-700 nanometer, where the Casimir force is negligible, then we can fit the data to extract the parameter like contact potential and spring constant. But by using this, why we did for the silicon carbide, the data was not in agreement with the thermal tuning, which shows that application of this equation, which is for using for metal conductor, is not rigorous application is not possible for poor conductor like a silicon carbide. Therefore, because we just needed the spring constant from the system, we used gold coated. We used the gold plate instead of silicon carbide, and then we did the process again, and from here we extracted a spring constant with 3% accuracy. So as from that formula, we saw that if we take a look at this term, the force, depending on the force on this term, show that the deflection gonna have a parabolic behavior. So we applied the voltage in this range, and then we plotted the cantilever deflection versus applied potential. So here I plotted in the same sphere plate separation for different sphere plate separation, and as we see that the minimum deflection from the equation, from the previous equation, we expect that when the potential is equal to the contact potential, we should have the minimum forces. But this force not necessarily zero, as we see here. We have this term. So then we use the several data points from this function, and we fit the data by this function, which has the extra term, which is this term is just coming, is net, it's effect of the net charge trapped on the silicon carbide sample. So this charge is difficult to interpolate, to interpret it numerically. Also, it's not for, because of the finite plate dimension, we couldn't use the PFA. So we fit the deflection with considering the weakest logarithmic function, and as we see that the deflection has a good agreement with the data, with the function we use. So with the fitting the data, we obtain the parameters C1 and C2, and then we have this function, which is its effect of the uncompensated remnant charges. So another term, important factor we extract from the data, it's contact potential, because of the different work function of the sample. So this high value for silicon carbide shows that the significant contribution of patch potential to the total force and origin of the deviation between theory and experiment. To prove the data from electrostatic measurement, also we use the KPFM, Kelvin probe force microscopy, for the different sample, which as you see here, I also put the arrow as an eye guide. So the peak-to-peak variation is comparable in magnitude with what we extract from the electrostatic measurement, about 600 millivolt. After all, then we can, by knowing the spring constant precisely and reducing all of the non-linear signal contribution and the effect of the patch potential, effect of the remnant electrostatic charges. Here we plot the experimental result for Casimir forces in compared to the Lifshitz theory. So we have quite good agreement in the range above 60 nanometer. So here between 60 and 100 nanometer, we fit the data with the average power law, which we're going to use to estimate the relative error. So here the absolute difference we got between the theory and experiment. But what should take into account that because of uncertainty, if we just consider 1 nanometer uncertainty in the separation between the sphere and plate, and because of a spring constant 0.5, then at the 8 nanometer, when we have jump to a contact, this relative error has become about 31%, and at this point, 100 nanometer, we have about 5% relative error. So by considering this fact, this relative error, then we can see quite our experimental result has quite good agreement with the theory. So this high value for contact potential also implies that electrostatic compensation will be necessary for device actuation. That's why we did here. So we consider the system as it is, like a sphere plate. We did the force measurement with the AFM. So what we model, so we consider all the forces involving in the system. So term of the Casimir, term of the electrostatic force, and the remnant charges, and considering the intrinsic dissipation in the system. So to obtain equilibrium point of the motion from this equation, we can define the parameter, bifurcation parameter, which is give us the ratio, the importance of the one force in compared to the other force, which is here is independent of the applied potential. So here the red one is show if we don't compensate the contact potential, and the blue is after compensation. So shows that so we have a stable and unstable port. This right side, which is close to the this left side, more close to the plate, and then in this range we're going to have stiction. Here, although the difference here seems not really significant, but using phase portrait show that the significant sensitive dependence on the contact potential. What we see here, phase portrait, which is the velocity of the system versus the distance. When we apply, when we compensate the contact potential, we have a closed orbit, which shows that the spring constant is strong enough to counterbalance the other forces. But if we don't compensate, it's the red one, which shows that the sphere went to the stiction, so the system is unstable. So in conclusion, we measured the Casimir force for first quantitative Casimir force measurement for silicon carbide sample down to the 10 nanometer, because we use very smooth surfaces. We saw that always there are uncompensated remnant electrostatic charge present on the sample, and we saw that the knowledge of Casimir and electrostatic force both is important for device actuation in the range below 200 nanometer if Casimir force want to have a dominant role. We use that dynamic analysis. It showed that silicon carbide, how it can enhance the regime of stability against the stiction. And we saw that from the last slide that compensation of contact potential is necessary for operating device to reduce stiction and stability. So that was my presentation.
Questions?
Was your silicon carbide from single crystal, or is it polycrystalline, or do you know?
We got actually we just the information of this with 400 micrometer thickness, because it's mechanical and chemical polished nitrogen doped silicon carbide.
But is polycrystalline or polycrystalline? Do you know?
I don't know that's
Single crystal or
polycrystal.
Okay. Yeah. Okay.
You showed this logarithmic dependence in potential, in electrostatic force.
Yeah.
And you also showed that the difference between the Lifshitz result and your measurements, basically, yeah, exactly here, points approximately 30% with close distance.
Yeah.
Have you tried compensating the electrostatic force dynamically by measuring the second derivative using an SE potential?
So,
Because then you could basically get this to zero. We have done that in experiments.
I mean, what we got this data, we got it experimentally and will be extracted also in the short range. So we'll consider this effect even in the short range, which was not really significant, but still we see that it has effect on the data.
Are you subtracting that from your data, or?
Yeah, it's from experimental data.
Okay.
Yeah, directly from.
Just this slide, you consider this additional cost as cost due to uncompensated charge.
Yeah.
But there is also contribution from the Casimir force, especially at shorter separation. Maybe if you attribute all this to the force due to the uncompensated charges and then subtracted this force, you increase a bit your result for measuring the Casimir force as a result. And this leads to larger deviation of theory and experiment at shorter separation.
Yeah, experimental, I mean, as I said, in the short range, I subtracted from the experimental data. I considered it.
Yes, but we all the additional force attribute to the uncompensated charges. And but here is the part due to the Casimir interaction. And by this reason, you overestimate the uncompensated
Galina, the
charges.
ranges are 1 microcouple, 500 nanometers above.
Yes, but even just at this reason, you overestimate the contribution of this charge. And then to smallest, it will be overestimated when subtracted.
Yeah, but that's, I think, because it's a really large range. This range, we didn't consider.
Last question.
Thanks. I was wondering, with the Kelvin probe that you were showing, you had, I guess, a kind of peak-to-peak value went from 0 to 600 or 700 millivolts. I was wondering what the kind of average value of it is and how that compares to the V0, because it looked like the V0 was close to the peak value that you get. And I find that a little confusing. I was thinking that it might have been something more like an average value.
Yeah, this because I did the measurement in the vacuum. This one also I did inside the vacuum, but outside, as also you mentioned, it would be a little bit lower because of the somehow the butter, thin butter like can compensate. But also it was close. But this is the that's the peak to peak. For the scan size about 1 micrometer.
Okay, and so I see that these measurements were made in vacuum or in air.
These are in the vacuum.
Okay, and the measurements were as well?
Yeah, both in the vacuum.
Okay, let's thank Mehdi. The next speaker is Irina Piroshenko, and she's going to tell us surface plasmons in perfume at 0 and 110